Now that we've learned how to find the Thevenin equivalent circuit for any linear circuit, let's look at a consequence of Thevenin's theorem, which is called the maximum power transfer theorem. And in order to understand how this works, we first have to understand how Thevenin's theorem works. So now that we know that, let's look at this particular question. Let's assume we have a circuit. And this is a linear circuit. And this linear circuit represents an electric generator with the distribution network, the wiring that it takes to get the power from the generator to, for example, a customer or to a load. So this is our electric generator. Plus a distribution network. And an example of this, a distribution network, would be, for example, the power lines that get power to your home. So let's assume that we have power, and this power is going to a load, and we're going to assume we've got a load resistance as our load, R sub L. Okay, so the distribution network we're talking about here is going to have an intrinsic resistance. I mean, unless you make it out of superconductor, which we can't really do, not for practical room temperature applications, but the distribution network will have some intrinsic resistance. And the thing about that intrinsic resistance of that distribution network is that intrinsic resistance is going to dissipate power. So I've got an electric generator, it's producing electric power. We have to get the power from the generator to the load, and to do that we have to use wiring to do that. But wiring has resistance. And because it has resistance, part of the electrical energy is going to be dissipated in that network while you try to get the power from the generator to the load. Obviously this is undesirable, but at the same time it's also something that we really can't avoid. Not until, of course, you can come up with a way of building room temperature superconductors. So in this case, we have undesirable wasted power. Now, what we want to do is this. We can't change the generator or the distribution network. Those are fixed. But what we want to do is we can change RL. We can change the value of RL. What we want to do is we want to choose a value of RL to maximize the amount of power that is dissipated in that load. So I want to maximize P sub RL, the power in the load. Here's the question. What value of RL does this? So if you think about it, I could kind of plot power versus resistance. So for example, I could do a plot like this. If I were to plot R sub L versus the power in R sub L, and I'll kind of create a plot where it's 0 at one part of the scale and infinity at the other. So this represents if the load resistance is just a wire, a short circuit. And when it's infinity, that represents if the load resistance is an open circuit. Well, if you think about it, If the load is a wire, I squared R is equal to 0. And so at 0 ohms, at a short circuit, obviously I'm not dissipating any power. At the other end of the extreme, if RL is infinity, then the current's equal to 0. It's an open circuit. And once again, I squared R is equal to 0. So at the short circuit and open circuit values for the load resistance, clearly the power is 0. If I were to look at a non-zero value that is less than infinity, then what I will see is I'll see this kind of function. I will see an increase in power from 0, and as I make the resistor larger and larger, it will roll off until finally when I get to an open circuit, then my power goes back to 0 again. So at some point along this graph, I'm going to hit PRL max. What is the value of R sub L that causes that to happen? And this is what the maximum power transfer theorem is all about. Okay, in order to analyze and understand how this circuit works, what we're going to do is we're going to apply Thevenin's theorem. We're assuming that's a linear circuit. Let's transform this circuit into its Thevenin equivalent. So in this case, I'm going to assume that our generator and distribution network can be transformed into the Thevenin equivalent circuit of VTH and RTH. With my load resistance. So once again, remember, VTH and RTH are fixed. We can't change those. That is part of the generator, part of the distribution network. This represents those, the Thevenin equivalent voltage and resistance. But I can change the load resistor. So let's do a little calculus here to figure out what value of RL gives us maximum power. And in this case, I'm going to assume that there is some current flowing around the loop of this simple circuit. And I'm going to call this current I sub L because it's obviously the current flowing through the load resistor. And I sub L, by Ohm's law, will just be equal to VTH over RTH plus RL. So that's easily calculated. Therefore, the power in that load resistor must be equal to IL squared times RL, once again using the definition for power in a resistor, which will therefore be equal to VTH over RTH plus RL squared times RL. So here's our expression for the power in that load resistor. But now I need to find the maximum value. And how do we do that? Well, you've learned this if you took a calculus course, right? How do you find the maxima or minima of a particular function? You take the derivative and then you set it equal to 0. And that's exactly what we're going to do here. We're going to find the derivative of PRL with respect to RL. So the partial derivative with respect to RL, knowing of course that RL is really the only quantity that we can change. So everything else will be fixed. All right? And then set this derivative to 0. So basic calculus, okay? One of the fundamental little tricks we learned in calculus. So in this case, taking this expression I'm going to use the chain rule on this. This will be equal to VTH over RTH plus RL squared minus 2 times VTH squared times RL over RTH plus RL to the third power. So I've just taken that derivative, I get this result, and I set it equal to 0. So from here, what do we get? Well, if this is equal to 0, then VTH squared over RTH plus RL squared will be equal to 2 times VTH squared times RL over RTH plus RL to the third power. And very nicely, some things fall out for us here. The VTH squared cancels. This cancels, and I'll just get rid of the third power here on this side. And so what we will wind up with then is that multiplying by this denominator on both sides, what we'll get is that RTH plus RL is equal to 2 times RL, or RTH is equal to RL. And that is our requirement. That is what gives us the maximum value of power, when RTH is equal to RL, or actually RL is equal to RTH. And so that's the result of maximum power transfer. The maximum power transfer theorem says to maximize PRL, set RL equal to the Thevenin equivalent resistance of the circuit you are getting the power from. RL is equal to RTH. So pretty straightforward. Let's do a simple example to apply this concept and see how it works. Assume we had a circuit like this. Okay, so I've got a simple circuit here, just a source and 2 resistors. I've got a load resistor connected across terminals A and B. And I want to find PRL max. And also the value of RL that maximizes PRL. So the first step is I'm going to do a Thevenin transformation of this circuit. And to do that, I'm going to remove the load. So first I need my open circuit voltage, VOC, and in this case it's pretty straightforward. Here's my VOC. And this is a really simple circuit. In fact, this is really nothing more than a voltage divider. VOC will just be equal to 150 divided by 30 plus 150 multiplied by 360. and that will be equal to 300 volts. And that, of course, is our Thevenin equivalent voltage. For our Thevenin equivalent current, RTH, I'm just going to zero out that independent source. It becomes a wire. So I have 30 ohms, 150 ohms, and now the equivalent resistance between these two nodes is 150 in parallel with 30, and that will be equal to 150 times 30 divided by 150 plus 30 is equal to 25 ohms. And that is equal to my Thevenin equivalent resistance. All right, so I'm just going to come back and substitute my Thevenin equivalent circuit. This now becomes 25 ohms. And now my Thevenin equivalent voltage is 300 ohms. So I've performed the substitution, the Thevenin substitution for the circuit. And RL must therefore also be equal to 25 ohms. It must be equal to the value of RTH. So my value is 25 ohms. What's my power? Okay, so in this case, this is easy to calculate. The book has formulas that you can memorize or write down, but there's no point to it. Anybody can easily figure out what the power is going to be from a simple circuit like this. And so in this case, I've got my load voltage VL. VL is just going to be equal to 25 over 25 plus 25 times 300. Will be equal to 150 volts. Once again, just using voltage division. And therefore, PRL is just equal to 150 volts squared divided by 25, V squared over R, and that's equal to 900 watts. All right, now you note the same currents flowing through both resistors, and they are the same resistance value, so therefore, the power of the Thevenin resistance is equal to 900 watts as well. And what's the power of the source? Well, the resistors generate 900 plus 900 is 1800 watts. We note then that the power of the source must be equal to minus 1800 watts. And you can easily prove this to yourself by calculating the power. So in this case, 300 divided by 50, I'll have 6 amps flowing around that loop. And by passive sign convention, that means I have to have minus 6 amps flowing in to that side, into the positive end. So minus 6 times 300 is minus 1800. So my power balance works. Now, I point this out, the fact that the Thevenin resistance has a power dissipation that's equal to the load power dissipation, because that is a consequence of the maximum power transfer theorem. What we note is, at maximum load power, the efficiency, which I represent as the power of the load divided by the magnitude of the power of the source, and that's just a definition for load efficiency, times 100%, That must be equal to 900 divided by 1800 times 100% is 50%. In other words, at maximum load power, half of the power is wasted in the distribution network. Which of course is represented by the Thevenin equivalent resistance. So maximum power transfer is actually not typically a desirable region of operation. You will see maximum power transfer matters in, for example, a lot of cases of radio frequency circuit design, where we're doing something called impedance matching, which is, really beyond the scope of this course. But you'll see it matters there. But when you look, for example, at the electric company giving us power, they do not want to waste electric power. They don't want to waste power in that wiring. So the electric company does not strive for maximum power transfer. The electric company strives for maximum efficiency. So really, the power company prefers to try to change this equation. And what the power company tries to do is both minimize RTH, minimize the Thevenin resistance, and also find a way to effectively increase the value of the load resistance. And this is done through techniques using the components called transformers. And you will also see, for example, that the power company will transmit power over long distances at very, very high voltages. And it turns out the reason for that is, once again, to allow them to minimize the power that is lost in that Thevenin equivalent resistance. So the power company tries to strive for no more than 5 to 10% of the energy that they produce actually being lost in the power lines. And if they could reduce that even further, that would be great. So the power company wants efficiency. They want to deliver as much of the generated power as possible to the customer, not to lose it in their own wiring. So maximum power transfer is an interesting theorem with limited applications. It's not something you normally see in large-scale power generation, just because it's not efficient. Okay? So that kind of wraps up our material now on Thevenin equivalent theorem. Now we're going to move to what I consider one of the most interesting parts of beginning circuits course, and that is the investigation and study of the operational amplifier. We'll see that next time.